So in this video, we're going to go over how to sketch the derivative of a linear function. And we'll look at two different ways that this might show up on an exam. So we're going to have two slides for this. So here's a linear function. Just like in the previous video, we want to remember that the derivative is the function that describes the slopes of the tangent lines. And we found the derivative by taking the limit as h went to 0 on the difference quotient, f of x plus h minus f of x, all over h. And then we also want to recall that the difference quotient just came from taking the slope of a line calculation, the delta y over delta x, that we've been doing probably since beginning algebra for calculating the slope of a line. And when we take the limit as h goes to 0, we are really finding the limit as delta x, the change in x, goes to 0 for the slope of a line calculation. So when I have a linear function, because the derivative is just the slope of a line calculation, the slope of the linear function is going to be the derivative. So when I look at this particular linear function, the first thing I want to notice is that the slope is negative because it's going downhill to the right. I know it's a negative slope, and I want to get a fairly accurate picture. The word sketch kind of has implicit to it the idea that there is some estimation going on in this process, but I do want to get it as reasonably accurate as I can. So I'm going to look at this and I'm going to say, well, it's negative, so I know the derivative has to be negative. I know f prime of x is going to be less than 0. I know the derivative is going to be a constant because the slope of a line is a constant real number. And then I could look at this and I could say, well, if the slope was -1, I would know that this line would make a 45-degree angle with the positive with the x-axis. And this angle looks to be greater than a 45-degree angle, so I know the slope's going to be more than -1. Where's -1 on here? Well, I have tick marks, but there's no numbers on there for scaling. So maybe this is a -1, maybe it isn't. If this had happened to be a -1, which it's not, then I could, then I could say, hey, I'm going to make the function a little below -1. In this case, this particular line has a slope of -2. I know that because I made the line in GeoGebra. But again, this is an estimation process. So you know it's negative. You know it's more than -1. So let's say I thought this was -1 right here. Then I might draw a line in a little bit less than -1, maybe a little further towards what I think might be a -2. I just go ahead and draw in my horizontal line at an estimated location that looks reasonably accurate based on what I have here. And then I want to recognize that the GeoGebra sketches, they never put the arrows on the lines. GeoGebra doesn't do that for me, but the arrows are there. And so when I draw the graph myself in a homework assignment, I should be including the arrows on the lines. I should be including the labels on the x and the y axes, those types of things. So I'm not going to give this a number because there's no numbers on the number line. And this is one way that a problem could be fed to you, where there's no context for you to identify number line labels. So you just have to do a little bit of estimation. So here the big idea is, hey, the derivative is going to be the slope of the line. The line has negative slope, so I know I have to draw a horizontal line that's a negative constant, and I don't know what it is, but that's what the sketch of it's going to roughly look like, and it's an estimate. The other way that a problem could be fed to you, again, this is a GeoGebra sketch, so it's not coming to us with the arrows that it should have. So if I were hand drawing it, I would make sure I had arrows everywhere. So the other way a problem can be fed to you if it's a linear function is you can be given numeric evidence that allows you to calculate the slope of the line. Hey, this is a linear function. I know the derivative of a linear function is the slope of the linear function. Hey, there's enough evidence here from the lattice points to actually find the slope. It's over 1 up 2. The slope of this line is m equals 2. So the derivative, if I name this function f of x, the derivative f prime of x is going to be 2 because the slope of this line is 2. So now, because I have a number lines, I can actually draw in the derivative, exactly what it's supposed to be, because I'm able to calculate it. So there it is, f prime of x is 2. There was enough numeric evidence to be able to get a number and use it.